Have you ever stopped to listen to the universe, not with your ears, but with your imagination, because out there, in the vast expanse of space, an eternal symphony is playing. Stars hum with energy, galaxies swirl in rhythmic motion, and cosmic forces weave together in a dance older than time itself. This isn't just poetry, it's science. The universe operates like a grand orchestra, every element perfectly tuned, every movement calculated, composing a masterpiece on a scale so immense, it's almost beyond comprehension. And today, we're stepping into the conductor's seat to unravel how this celestial symphony shapes the destiny of everything around us. Think of the last time music gave you chills the way a single note can swell into something overwhelming, something that feels alive. Now picture that same power, but stretched across billions of light years, where black holes drum the deep bass of gravity, supernovas crash like cymbals, and invisible dark matter pulls the strings of an unseen web that holds the cosmos together. This isn't just random chaos, it's a carefully balanced performance, one that scientists are only beginning to decode. From the way planets align in harmonic orbits to the eerie silence of empty space between them, every detail plays a part in this universal composition. What if I told you that you're part of this symphony too? Every atom in your body was forged in the heart of a star. Every breath you take connected to the same cosmic rhythm that guides galaxies. That's the magic we're exploring today, the breathtaking idea that the universe isn't just expanding, it's creating, evolving, and telling its own story through the language of physics and wonder. So sit back and let's journey together into the depths of space, where science meets artistry, and where the mysteries of celestial symphonies wait to be heard. By the end of this, you'll never look at the night sky the same way again. The universe doesn't just move, it breathes. Every spinning galaxy, every flickering star, even the silent drift of planets through the void, they all follow rhythms so precise. It's as if the cosmos itself is reading sheet music. Take gravity, for example. It's not just a force, it's the conductor of this grand orchestra, dictating the tempo of celestial bodies with invisible waves. When two black holes spiral toward each other, their collision sends ripples through space-time, a phenomenon scientists call gravitational waves. These aren't just random disturbances, they're literal notes in the universe's symphony, vibrations so low we needed instruments like LIGO to finally hear them after billions of years. Then there are pulsars, the universe's natural metronomes. These dense, spinning neutron stars beam radiation with such clockwork precision, they rival the most accurate atomic clocks on Earth. Imagine a lighthouse in space, flashing at intervals so regular you could set your watch by it. That's the kind of rhythmic order woven into the fabric of the cosmos. Even chaos has its role. Supernovas might seem like explosive crescendos, but they scatter the very elements that birth new stars, turning destruction into creation. But here's what's truly mesmerizing. This symphony isn't just playing out randomly. There's a delicate balance, a fine-tuning so exact that even slight changes would unravel everything. The expansion rate of the universe, the strength of fundamental forces, they're all calibrated like instruments in an orchestra, each adjustment critical to the harmony of the whole. Some call it the Goldilocks Principle, conditions not too hot, not too cold, but just right for life to emerge and the music to continue. And just like a symphony builds toward a climax, the universe, too, is evolving, its composition shifting as galaxies drift apart and dark energy stretches the very fabric of space-time. So when we look up at the night sky, we're not just seeing stars, we're witnessing a performance billions of years in the making, one where every particle, every force, plays its part in a melody written by the laws of physics. And the most astonishing thing, we're not just the audience, we're part of the chorus. Picture a stellar nursery, a vast, swirling cloud of gas and dust where gravity plays the role of both composer and conductor. In these cosmic cradles, pockets of material slowly collapse, drawn together by an invisible force until the pressure becomes so intense that nuclear fusion ignites. And just like that, a star is born, its first light bursting forth like the opening note of a symphony. These stellar nurseries, often nestled within glowing nebulas, aren't random or chaotic. They follow patterns as precise as musical scales, with each newborn star adding its unique timbre to the galactic chorus. Take the Orion Nebula, for example, a stellar factory visible even to the naked eye. Inside its glowing folds, hundreds of stars are taking shape, their formation governed by the same universal laws that dictate how sound waves travel through air. The densest knots of gas collapse first, giving rise to massive stars that blaze with intense heat, while smaller, slower forming stars hum along in the background. Together, they create a celestial harmony, a dynamic interplay of light and energy that shapes the structure of their galactic neighborhood. But stars don't just appear and vanish in isolation. They're born in clusters, bound together by gravity like instruments in an orchestra section. Over time, these clusters evolve, their stars drifting apart or merging in ways that mirror the ebb and flow of a musical movement. Some stars live fast and die young, exploding as supernovas and scattering heavier elements into space, ingredients that will one day form new stars, planets, even life itself. Others, like our Sun, settle into a steady rhythm, burning steadily for billions of years and providing the stable foundation around which planets can dance. Galaxies, too, follow this symphonic structure. Spiral arms swirl like melodies unfolding in space, their stars and gas clouds moving in synchronized orbits. Elliptical galaxies, dense and ancient, resonate like deep bass notes, while irregular galaxies add unpredictable yet mesmerizing flourishes. And just as a symphony builds toward a climax, galaxies collide and merge in cosmic crescendos, their stars weaving new patterns in the grand composition of the universe. This isn't just beautiful metaphor, it's observable science. The same mathematics that describe harmonic vibrations in music can predict the orbits of planets, the pulsing of variable stars, even the way galaxies spin. The universe doesn't just create stars at random. It composes them, each birth a note in an endless, evolving masterpiece. And as we learn to listen through telescopes, gravitational wave detectors, and space observatories, we're beginning to hear the music that's been playing since the dawn of time. If you've ever watched a pendulum swing or felt the steady pulse of a drumbeat, you've experienced rhythm in its simplest form. Now, imagine that same rhythmic precision, but scaled up to the size of a solar system. Planets don't just wander aimlessly through space. They move with a grace and predictability that would make even the most meticulous composer envious. Johannes Kepler, the astronomer who unlocked the secrets of planetary motion, didn't just discover laws, he revealed the universe's sheet music. His 3 laws of planetary motion show us that orbits aren't random paths but elegant ellipses, with stars acting as gravitational anchors and planets gliding along like notes in a cosmic melody. Take Earth's own journey around the Sun. Every 365 days, we complete a loop so consistent, we base our calendars on it. But here's what's even more astonishing. The farther a planet is from its star, the slower it moves, obeying Kepler's harmonies like a violinist following a conductor's tempo. A year on Mercury blurs by in just 88 Earth days, while Neptune's orbit stretches over a glacial 165 years. Yet, despite these differences, there's no chaos, only balance. The same gravitational forces that keep planets in check also create resonances, where orbits synchronize in perfect ratios. Jupiter's moons, for instance, dance in such precise harmony that for every orbit Ganymede makes, Europa completes exactly 2, and Io 4, a celestial waltz written in the language of mathematics. And it's not just our solar system. Thousands of exoplanets discovered in recent decades follow these same universal rhythms. Some orbit so close to their stars that a year lasts mere hours, while others drift in slow, sweeping arcs. But no matter the tempo, stability reigns. Even in binary star systems where planets navigate the pull of two suns, orbits find equilibrium, tracing figure-8 paths that defy their chaotic surroundings. This isn't luck, it's physics composing a symphony where gravity's invisible hand ensures every planet keeps its place in the score. The beauty of these cosmic rhythms isn't just in their precision, but in their endurance. Solar systems form from swirling disks of gas and dust where particles collide and clump over millions of years. Yet, against all odds, the result isn't chaos, it's order. Planets emerge with orbits spaced apart, their gravitational tugs avoiding catastrophic collisions, much like musicians in an orchestra adjusting their pitch to stay in tune. And just as a symphony builds toward a finale, these orbits evolve over eons, nudged by passing stars or the gentle drag of leftover dust, their melodies shifting but never faltering. So when you look up at the night sky, remember, those pinpricks of light aren't just scattered randomly. They're part of an intricate, ever-moving composition, where planets trace their paths with the same certainty as a metronome's tick, and the universe itself keeps time on a scale beyond human imagination. Now, let's talk about the unseen force holding this cosmic symphony together: dark matter. Imagine an orchestra where the conductor stands invisible, yet every musician feels their guidance, every note bends to their will. That's dark matter's role in the universe. It doesn't emit light, it doesn't reflect it, we can't see it at all. Yet, without it, galaxies would fly apart, cosmic structures would crumble, and the music of the spheres would fall into discord. How do we know it's there? Look at a spinning galaxy, and you'll notice something strange. The stars on the outer edges orbit just as fast as those near the center, defying the laws of gravity as we understand them. According to physics, those outer stars should be drifting away, slowed by distance, but they're not. Something invisible, something with mass, must be holding them in place, like an unseen hand keeping the rhythm steady. That's dark matter weaving a gravitational web so vast, it forms the skeleton of the universe itself. Think of it like this: if galaxies were notes on a sheet of music, dark matter would be the staff lines, invisible, but essential for keeping everything in harmony. When galaxies collide, their visible stars pass through one another like ghosts, but their dark matter leaves a gravitational fingerprint, bending light in ways we can measure. This phenomenon, called gravitational lensing, lets us map dark matter's presence like tracing the outline of a shadow. And what we've found is staggering. Dark matter outnumbers ordinary matter 5-1, a silent majority conducting the universe from the shadows. But here's the most fascinating part: dark matter isn't just holding things together, it's composing the universe's future. In the early cosmos, tiny fluctuations in dark matter's density acted like seeds, pulling gas and dust together to form the first galaxies. Without it, stars might never have ignited, and the cosmic symphony would have stalled before the first movement. Even now, as dark energy pushes the universe to expand faster, dark matter's gravity counterbalances, ensuring galaxies don't dissolve into the void. So while we may never see this mysterious conductor directly, we hear its influence in every gravitational wave, every spinning galaxy, every cosmic structure stretching across the void. The universe's symphony plays on not despite the darkness, but because of it. Black holes are the universe's ultimate maestros of contrast, simultaneously silencing everything that crosses their event horizon while orchestrating some of the most violent, energetic performances in the cosmos. Picture a violin string stretched to its limit, vibrating with such intensity that it warps the air around it. Now scale that up to a singularity where gravity bends space-time itself, twisting the fabric of reality into a gravitational vortex so powerful, not even light can escape. Yet, paradoxically, it's this same destructive force that fuels creation. When matter spirals toward a black hole, it doesn't just vanish quietly, it screams. Friction heats the gas and dust swirling into the abyss to millions of degrees, forming an accretion disk that glows brighter than entire galaxies. These disks don't just shine, they roar, emitting high-energy X-rays and jets of plasma that shoot across space at nearly the speed of light. These jets, stretching thousands of light-years, act like cosmic trumpets, blasting raw material into the void where it can seed new star formation. It's a breathtaking contradiction. Black holes obliterate matter, yet they also scatter the ingredients for new beginnings. And then there's the sound, or rather, the absence of it. At the event horizon, time slows to a crawl, stretching seconds into eons. A single note falling into a black hole would deepen infinitely, fading into silence as it crosses the point of no return. But just beyond that boundary, chaos reigns. The supermassive black hole at the center of our Milky Way, Sagittarius a star, may appear quiet now, but radio telescopes have captured its past outbursts, echoes of ancient feeding frenzies that once lit up the galaxy. Yet black holes don't just consume, they harmonize. Binary black holes, locked in a gravitational dance, spiral closer over millennia until they collide in a crescendo of gravitational waves. These ripples, first detected in 2015, confirmed Einstein's century-old prediction and opened a new way to hear the universe. Each collision is a cosmic drumbeat, sending vibrations through space-time that reveal the hidden rhythms of the cosmos. Perhaps most remarkably, black holes may even shape the destiny of galaxies. Their gravity dictates the motion of stars, and their outbursts can halt star formation by blasting away gas or trigger it by compressing cosmic clouds. They're the universe's regulators, balancing destruction and creation like a composer balancing silence and sound. So while they might seem like cosmic vacuum cleaners, they're really artists, sculpting the universe one cataclysmic note at a time. Among the universe's most mesmerizing timekeepers, neutron stars stand out like celestial drummers in the grand cosmic orchestra. Born from the explosive deaths of massive stars, these incredibly dense remnants pack more mass than our sun into a sphere no wider than a city. But what makes them truly extraordinary isn't just their size, it's their rhythm. Some spin hundreds of times per second, emitting beams of radiation so precise they rival the most advanced atomic clocks on Earth. Imagine a lighthouse spinning faster than a jet turbine, its light sweeping across space in perfect, predictable pulses. That's the heartbeat of a neutron star, a metronome set against the backdrop of the cosmos. These cosmic percussionists don't just keep time, they shape it. Take pulsars, a type of neutron star that beams radio waves with such regularity. Astronomers initially mistook their signals for artificial transmissions. The Crab pulsar, for instance, spins 30 times every second, flashing like a strobe light in the remnants of a supernova witnessed on Earth in the year 1054. Its rhythm is so unwavering, scientists have used it to test Einstein's theory of relativity, watching as its pulses arrive milliseconds earlier or later when passing through warped spacetime near massive objects. It's as if the universe itself is using these spinning relics to reveal its hidden mechanics. But neutron stars don't just tick quietly in isolation. Their gravitational pull is so intense, it distorts the fabric of space around them, creating ripples that can alter the orbits of nearby stars. In binary systems where two neutron stars spiral toward each other, their dance culminates in a spectacular collision, a cosmic drumroll that unleashes gravitational waves, gold-forging kilonovas, and gamma-ray bursts bright enough to outshine entire galaxies for a fleeting moment. These events aren't just fireworks, they're the universe's way of recycling matter, scattering heavy elements like platinum and uranium into space, the very elements that make up our jewelry, our technology, even parts of our bodies. Yet even alone, a neutron star's influence is profound. Their magnetic fields, trillions of times stronger than Earth's, can strip atoms apart and accelerate particles to near light speeds, creating auroras visible light years away. Some, called magnetars, suffer starquakes, violent crust fractures that release energy equivalent to 1 billion hydrogen bombs, sending shock waves through the interstellar medium like a cymbal crash echoing in the dark. What's most humbling is how these tiny, spinning titans connect us to the larger symphony. The iron in your blood, the gold in your wedding ring, they were forged in the hearts of stars and scattered by neutron star collisions long before Earth existed. Every pulse, every ripple, every cataclysmic merger is a reminder that the universe doesn't just move, it keeps time, composes, and recreates itself in rhythms we're only beginning to understand. So the next time you check your watch, remember, somewhere out there, a neutron star is ticking too, its beat echoing across the ages. There's a moment in every great symphony where the music swells to an earth-shaking climax, a finale so powerful it leaves you breathless. Now imagine that same intensity, but multiplied by the force of a star's death. Supernovae are the universe's explosive finales, cataclysmic eruptions that mark the end of a massive star's life while scattering the seeds of new beginnings across the cosmos. These aren't just random bursts of destruction, they're precision-engineered events, nature's way of recycling stardust into something greater. Take the famous Crab Nebula, the remnant of a supernova observed on Earth in the year 1054. For weeks, it shone brighter than Venus, visible even in daylight, a stellar swan song echoing across 7,000 light-years. But what's left behind is just as breathtaking, a swirling tapestry of gas and dust, enriched with heavy elements like iron, gold, and uranium. These aren't just cosmic leftovers, they're the raw materials for future stars, planets, even life itself. Every time you breathe, you're inhaling oxygen forged in a supernova's heart. Every time you hold a piece of jewelry, you're touching atoms born from a star's violent death. What makes supernova so extraordinary isn't just their power, it's their timing. A star spends millions or billions of years fusing hydrogen into helium, then helium into carbon, step by step up the periodic table like a musician practicing scales. But when it reaches iron, the music stops. Iron can't fuse without sucking energy away, causing the star's core to collapse in seconds. The outer layers crash inward, then rebound in a shockwave so violent, it outshines entire galaxies for weeks. This explosion doesn't just destroy, it transforms. Temperatures soar to billions of degrees, forging elements heavier than iron in a single, chaotic crescendo. And just like a symphony's finale lingers in the air, supernova leave echoes we can still detect centuries later. The Veil Nebula, a remnant 6,000 light-years away, glows with the ghostly light of ionized oxygen and sulfur, a spectral encore from a star that died 20,000 years ago. Even the solar system bears witness. Radioactive isotopes buried in Earth's crust reveal traces of nearby supernova that erupted just as life was beginning here. These explosions aren't just distant spectacles, they're part of our origin story. Yet the most remarkable thing about supernova isn't their destruction, it's their creativity. The shockwaves from these blasts compress nearby gas clouds, triggering the birth of new stars like cosmic dominoes. Our own sun may owe its existence to a long-ago supernova, its shockwave nudging a cloud of dust to collapse and ignite. It's a cycle as old as the universe itself. Stars live, die, and from their ashes, new stars rise. The cosmos doesn't just endure, it reinvents, composes, and plays on. Galactic collisions sound like the ultimate cosmic train wrecks, catastrophic events where stars crash, gas clouds shred, and entire galaxies distort beyond recognition. But here's the twist: these collisions aren't destructive finales. They're creative rebirths, the universe's way of composing new structures from chaos. Picture two orchestras merging mid-performance, their instruments clashing at first, then gradually harmonizing into something richer, more complex. That's what happens when galaxies meet. Their stars, spaced so far apart, rarely collide. Instead, they slide past one another like dancers in a cosmic ballet, pulled into new orbits by gravity's invisible hand. Take the Milky Way and Andromeda, for example. Right now, they're hurtling toward each other at 250,000 miles per hour, destined to merge in about 4 billion years. When they do, their spiral arms will stretch into streaming tails of stars, a phenomenon astronomers call tidal disruption. Gas clouds will compress, igniting bursts of new star formation, stellar fireworks lighting up the collision zone. Yet despite this violence, the result won't be a scattered mess. Over eons, the two galaxies will settle into a single, smooth, elliptical galaxy, their stars now orbiting in a shared rhythm. But the real magic happens in the details. During collisions, supermassive black holes at the galaxy's centers spiral toward each other, their gravitational pull flinging stars into wild new trajectories. Some stars might even get ejected entirely, streaking across intergalactic space like rogue notes escaping a melody. Meanwhile, shockwaves ripple through galactic gas, triggering the birth of massive star clusters, cosmic crescendos that outshine entire galaxies for millions of years. The antennae galaxies, caught mid-collision 700 million light-years away, showcase this beautifully. Their long, arching tails of dust and young blue stars resemble musical notes frozen in space, a snapshot of dissonance resolving into harmony. What's astonishing is how these events sculpt the universe's large-scale structure. Collisions redistribute matter, building galaxy clusters that thread through the cosmos like beads on a string. They're also cosmic recycling plants. The turbulent mixing of gas during mergers enriches galaxies with heavy elements, seeding future generations of stars and planets. Without these collisions, the universe would lack the raw materials for life as we know it. So while galactic mergers might seem violent, they're ultimately symphonic, chaotic movements that give way to new order, proving once again that the universe doesn't just create. It composes. Close your eyes and imagine tuning an old radio, static crackling as you search for a faint, distant station. Now picture that same static, but instead of random noise, it's the faintest whisper from the dawn of time itself. That's the cosmic microwave background, the afterglow of the Big Bang, a relic so ancient it's often called the universe's first light. But here's the twist: it's not just light. It's the opening chord of the cosmic symphony, a vibration stretched thin over 13.8 billion years, carrying secrets about how everything began. This radiation wasn't discovered by accident. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent hiss in their antenna, a noise they initially blamed on pigeon droppings. After scrubbing the equipment clean, the static remained. What they'd stumbled upon was the cooled remnant of the Big Bang's fiery birth, now just 3 degrees above absolute zero. Think of it like embers from a colossal explosion, once blazing at trillions of degrees, now faded to a whisper. But within that whisper lies a treasure trove of data, a snapshot of the universe when it was a mere 380,000 years old. What makes this cosmic hum so extraordinary is its near-perfect uniformity, like a single sustained note played across the entire sky. Yet, if you listen closely, or rather, if you map it with satellites like COBE or Planck, you'll detect tiny fluctuations, variations in temperature no larger than 1 part in 100,000. These aren't imperfections, they're the universe's first murmurings of structure, the seeds from which galaxies, stars, and eventually we would grow. Without these slight density variations, gravity would have had nothing to grip, and the cosmos would have remained a featureless sea of particles. But the cosmic microwave background doesn't just tell us about the past. It's a tuning fork for the present. By measuring its polarization, the way its light waves vibrate, scientists have confirmed the universe's age, composition, and even the existence of dark energy. It's how we know ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos. The rest, dark matter and dark energy, the invisible conductors shaping the universe's expansion. Perhaps most poetically, this radiation is the closest thing we have to a universal lullaby. It's the echo of a time when the universe transitioned from a scorching, opaque plasma to a transparent expanse, finally allowing light to travel freely. Every direction we look, we're met with this primordial glow, a reminder that we're all bathed in the same ancient light. So the next time you see static on an old TV screen, remember, you're glimpsing the universe's oldest melody, a song that began before time had meaning and continues to hum in the spaces between everything. Einstein's general theory of relativity didn't just redefine gravity, it gave the universe a voice. Hidden in his equations was a prediction so radical, even he doubted it could ever be proven: the existence of gravitational waves, ripples in the fabric of space-time itself. For a century, these waves remained theoretical, as elusive as a whisper in a hurricane. Then, in 2015, humanity finally listened. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal from a pair of black holes colliding 1.3 billion light-years away. The event lasted less than a second, but it changed astronomy forever. For the first time, we weren't just seeing the cosmos, we were hearing it. Think of space-time as the surface of a pond. When a pebble drops, concentric rings spread outward, distorting the water's surface. Now replace the pebble with 2 black holes, each dozens of times heavier than our sun, spiraling toward each other at half the speed of light. Their collision sends shockwaves through space-time, stretching and squeezing everything in their path, including the Earth itself. By the time these waves reach us, the distortion is minuscule. LIGO detectors measured shifts 10,000 times smaller than a proton. Yet that faint tremor carried the signature of an event more powerful than all the stars in the observable universe, shining simultaneously for a moment. What's astonishing isn't just that we detected these waves, it's what they've revealed. Gravitational waves pass through matter unimpeded, unlike light, which can be absorbed or scattered. This means they carry pristine information from the most violent, hidden corners of the cosmos. When neutron stars collided in 2017, the resulting gravitational waves arrived alongside a gamma-ray burst and a kilonova, a multi-messenger event that confirmed these collisions forge heavy elements like gold and platinum. Suddenly, we understood that the ring on your finger or the chip in your phone contains stardust forged in a cataclysm older than Earth. But the symphony doesn't stop there. Gravitational waves come in different frequencies, each tuned to different cosmic events. Supermassive black hole mergers with masses billions of times our sun's produce waves so low-pitched they take years to oscillate. Future space-based detectors like LISA will hunt these deep hums, while pulsar timing arrays using neutron stars as natural metronomes could detect the background murmur of countless black hole mergers across cosmic history. Together, they'll compose a gravitational wave spectrum, from the shrill chirps of stellar mass collisions to the basso profundo of primordial ripples from the Big Bang itself. And here's the most thrilling part: we're just learning to listen. Every new detection rewrites the rules. Some black hole mergers defy expectations, with spins misaligned like discordant notes. Others reveal intermediate mass black holes, a long missing link in cosmic evolution. With each event, the universe whispers secrets we couldn't uncover any other way, proof that space isn't silent, but vibrating with the echoes of its own creation. So while light paints the cosmos in color, gravitational waves score its rhythm, turning the universe into a concert hall where even the quietest vibrations tell a story. If the cosmic symphony were perfectly predictable, every note would land exactly where we expect. Stars would form in flawless patterns, galaxies would spin with mechanical precision, and the universe would unfold like a pre-written score. But that's not how the universe works. Beneath the grand movements of gravity and light lies a hidden layer of chaos, an improvisational solo played by the rules of quantum mechanics. At the smallest scales, particles don't follow strict rhythms. They flicker in and out of existence, collide unpredictably, and tunnel through barriers as if the laws of physics were mere suggestions. This quantum unpredictability isn't a flaw in the cosmic composition, it's the spark that makes creation possible. Consider the birth of a star. Before gravity can sculpt a gas cloud into a glowing sphere, tiny quantum fluctuations must first create the seeds of density. These microscopic ripples, smaller than atoms, grow over millions of years, pulling matter together until nuclear fusion ignites. Without these random quantum nudges, gas clouds might drift forever, never collapsing into stars. Even the vast cosmic web, with its filaments of galaxies stretching across the void, owes its structure to quantum noise amplified by inflation in the universe's first moments. What began as subatomic jitters became the blueprint for everything we see. But quantum mechanics doesn't just build, it disrupts. Take vacuum energy, the seething foam of particles and antiparticles that pop in and out of existence in empty space. This isn't just theoretical, it's measurable. The Casimir effect, where two metal plates placed microscopically close feel an invisible push from quantum fluctuations, proves that nothingness is alive with activity. On cosmic scales, this energy might even drive the universe's accelerating expansion, a dark energy crescendo no one saw coming. The most breathtaking quantum improvisation, though, happens inside stars. Fusion relies on quantum tunneling, where protons overcome their mutual repulsion not by brute force, but by vanishing and reappearing on the other side of an energy barrier, a cosmic magic trick that powers every star in the sky. Without this quantum sleight of hand, the universe would be cold and dark, its hydrogen fuel forever locked away. So while gravity conducts the symphony and dark matter holds the score, quantum mechanics is the jazz musician in the cosmic band, unpredictable, inventive, and utterly essential. It reminds us that the universe isn't just playing a predetermined melody, it's making it up as it goes, one spontaneous, shimmering note at a time. What if our universe isn't the only one composing a grand symphony? Some of the boldest theories in physics suggest we might be just one verse in an endless cosmic chorus, a single melody among infinite parallel realities, each playing its own unique tune. This is the multiverse hypothesis, a concept that stretches our understanding of existence to its limits. Picture an orchestra where every possible variation of the universe's fundamental laws is performed simultaneously, some with stronger gravity, others with faster light, or even entirely different particles. In one universe, stars might burn out in seconds. In another, they could shine forever. The implications are as dizzying as they are profound. Take the inflationary multiverse theory, born from the idea that our universe underwent rapid expansion moments after the Big Bang. If space-time stretched unevenly, pockets of it could have pinched off into separate universes, each with its own physics. Like bubbles forming in a boiling pot, these universes would float in a vast cosmic foam, forever out of reach. String theory takes this further, suggesting extra dimensions curled into shapes that define each universe's laws, a cosmic kaleidoscope where every twist creates a new harmony. But how would these parallel symphonies interact, if at all? Some models propose rare collisions between universes, leaving faint imprints in the cosmic microwave background, like echoes of a distant orchestra bleeding into our own. Others suggest that quantum mechanics' strange probabilities aren't just random, but reflections of every possible outcome playing out across countless realities. In one universe, you might be reading this script, in another, you're composing it. The multiverse isn't just science fiction, it's a serious attempt to explain why our universe seems so finely tuned for life. If countless universes exist with random laws, it's no surprise we find ourselves in one where the conditions are just right. But here's the catch: we may never observe another universe directly. Their music would be forever muted to us, leaving only mathematical elegance as our clue. Yet the idea reshapes our place in the cosmic symphony. No longer the soloist, our universe becomes one voice in a choir beyond comprehension. A humbling reminder that the grandest melodies might still lie beyond our ears. The universe is vast beyond comprehension, trillions of galaxies, each brimming with billions of stars, countless planets circling them in the Goldilocks zones where life could thrive. With numbers so staggering, the cosmic symphony should be teeming with voices. So where is everybody? This haunting question, posed by physicist Enrico Fermi over half a century ago, cuts to the heart of one of astronomy's greatest mysteries. If life is even remotely common, the Milky Way alone should host thousands of civilizations. Yet our radio telescopes hear only silence, as if the universe is a grand concert hall where we're the sole audience. One explanation is chillingly simple: we might be the first. The universe spent its early epochs too hostile for complex life, filled with violent gamma-ray bursts and colliding galaxies. Only in the last few billion years have conditions stabilized enough for life to emerge. If intelligent civilizations take time to evolve, we could be among the earliest arrivals, lonely pioneers in a cosmos still waking up to its own potential. Or perhaps civilizations don't survive their technological adolescence. The Great Filter theory suggests some catastrophic barrier: nuclear war, runaway AI, ecological collapse prevent societies from advancing far enough to colonize the stars. If true, humanity's fate hinges on whether we're past this filter or barreling toward it. The eerie silence could be a graveyard of civilizations that burn too bright, too fast. But there's another possibility: we're listening wrong. Imagine ants trying to detect Wi-Fi signals. Their senses aren't tuned to the right frequencies. Advanced civilizations might communicate using neutrino beams, quantum entanglement, or structures we can't yet conceive. The Breakthrough Listen project scans millions of stars for radio waves. But what if extraterrestrials abandoned radio millennia ago, moving to technologies as invisible to us as radio would be to the Middle Ages? Then there's the zoo hypothesis, the idea that other civilizations know we're here but choose not to interfere, observing us like wildlife in a cosmic preserve. Or the dark forest theory, where every civilization hides, fearing that any broadcast could attract predators. In a universe where survival is paramount, silence might be the only safe strategy. Yet the most hopeful answer might also be the simplest. Space is unimaginably vast. Even at light speed, signals from the nearest stars take years to reach us, and the Milky Way spans 100,000 light-years. We've barely begun our search, like dipping a cup into the ocean and concluding it contains no fish. The symphony might be playing all around us, its melodies too faint, too distant, or too alien for our ears to catch. The universe's silence isn't an answer, it's a question, one we're only beginning to learn how to ask. Why does the universe seem to play a melody so perfectly tuned for life? The air we breathe, the gravity that anchors us, even the delicate balance of forces that allow atoms to form, they all align with eerie precision, as if the cosmos itself were designed for listeners. This isn't just poetic wonder, it's the heart of the anthropic principle, the observation that the laws of physics appear meticulously calibrated to make our existence possible. Change just one note in this cosmic score, strengthen gravity by a fraction, tweak the charge of an electron, or alter the expansion rate of the early universe, and the symphony collapses into silence. No stars, no planets, no life. Take the cosmological constant, the energy density of empty space. If it were slightly higher, the universe would have expanded too rapidly for galaxies to form. Slightly lower, and everything would have collapsed back into a black hole long ago. Instead, it's balanced on a knife's edge, fine-tuned to 1 part in 10 to the power of 120, a number so incomprehensibly precise, it's like threading a needle with a thread as wide as the observable universe. Or consider carbon, the element essential for life as we know it. Its creation relies on a rare resonance in stellar nuclear reactions, a precise energy level that allows 3 helium nuclei to fuse together inside aging stars. Without this exact match, carbon wouldn't exist in meaningful quantities, and neither would we. Even the strength of the strong nuclear force which binds atomic nuclei is dialed to perfection. A few percent stronger, and hydrogen would vanish early in the universe's history. A few percent weaker, and complex elements couldn't form at all. So how do we explain this breathtaking fine-tuning? One answer is sheer chance, a cosmic lottery where we just happen to win. But the odds are so vanishingly small, it's like flipping a coin and getting heads 1 trillion times in a row. Another possibility is the multiverse, an infinite ensemble of universes, each with different physical constants, where only the rare few capable of hosting life ever notice their own existence. In this view, we're not special, just statistically inevitable. Yet there's a third, more provocative interpretation, that the universe is somehow meant to be observed. Not necessarily by a traditional designer, but by the simple fact that consciousness shapes reality as surely as reality shapes consciousness. Quantum mechanics already hints at this with the observer effect, where the act of measurement alters the state of particles. Could the universe, in some deep way, require observers to bring its symphony into focus? The anthropic principle doesn't provide easy answers, but it reframes the question. Instead of asking why the universe suits us, we might ask what our presence reveals about its true nature. After all, a symphony unheard is just vibrating air. But when listeners arrive, the music takes on meaning. Perhaps we're not just accidental witnesses to the cosmic performance, we're part of its crescendo. Time flows like a river with no reverse, carrying the universe forward in a relentless, one-way march. Unlike a symphony that can be rewound and replayed, cosmic time refuses to loop backward, each moment etching itself permanently into the fabric of existence. This isn't just a poetic observation, it's a law of physics, entropy, the measure of chaos in a system always increases, ensuring the universe's score never repeats the same measure twice. Think of it like a sandcastle on the shore. No matter how carefully you build it, the tide of time will eventually scatter the grains, leaving no trace of the original structure. The universe operates the same way, trading order for disorder in an irreversible dance. Take the birth and death of stars. A young star burns bright, fusing hydrogen into helium in a delicate balance of gravity and pressure. But over billions of years, its fuel depletes and entropy takes over. For massive stars, this means a cataclysmic supernova, scattering their guts across the cosmos. For smaller stars like our Sun, it's a slower fade into a white dwarf, then a cold, dark remnant. No matter the path, the outcome is the same. Energy disperses, structure decays, and the universe inches closer to a state of equilibrium where no more work can be done, a cosmic silence known as heat death. Yet entropy isn't just about destruction. It's the engine of creation too. Without it, gas clouds would never collapse into stars, and planets would never form from debris. The same chaos that dissolves old structures seeds new ones, like a composer tearing up an old manuscript to draft a fresh melody. Even life itself depends on entropy. Every breath you take relies on the breakdown of molecules to release energy, a process governed by the same thermodynamic laws that govern galaxies. What's fascinating is how this unidirectional flow shapes the universe's destiny. Gravity tries to pull matter together, creating pockets of order, galaxies, stars, planets, while entropy fights to disperse them. This tug-of-war defines cosmic evolution, from the first stars igniting in the early universe to the eventual evaporation of black holes trillions of years from now. The universe isn't just expanding, it's unraveling, its energy spreading thinner with every passing moment. But here's the twist: time's arrow might not be absolute. Some theories suggest that on quantum scales, particles can briefly defy entropy, appearing to move backward in time. And in the bizarre realm of black holes, where gravity warps spacetime beyond recognition, the usual rules of cause and effect blur. Could there be pockets of the cosmos where time's symphony loops or stutters? The answer, like so much in physics, remains just out of reach, a haunting cadence left unresolved. So while the universe's grand composition may be irreversible, it's far from monotonous. Every moment, from the birth of a star to the decay of a proton, adds a unique note to the score. And though the final movement might be silence, the journey there is anything but quiet. Imagine a tree falling in a forest with no one around to hear it. Does it make a sound? Now scale that up to the cosmos. If a galaxy spins, a black hole merges, or a star explodes with no conscious being to witness it, does it truly happen in the way we understand? This isn't just philosophy, it's a frontier where quantum physics and metaphysics collide, suggesting that consciousness might not merely observe the universe but participate in its very composition. At the heart of this idea lies the observer effect, a quantum quirk where the act of measurement changes the state of a particle. Electrons behave as waves until observed, then snap into defined positions, as if reality hesitates until someone looks. But could this principle extend beyond the lab? Some interpretations propose that the universe's grand symphony remains an indistinct hum of possibilities until consciousness crystallizes it into the reality we know. The ancient philosophical question, if a tree falls, takes on cosmic significance when applied to supernovas or spinning galaxies. Without an observer, do quantum superpositions, those ghostly states where particles exist in multiple places at once, persist indefinitely? The implications are staggering. Consciousness might be less like a passive audience and more like a co-conductor, its attention shaping the universe's melody note by note. This idea finds echoes in unexpected places. Biocentrism, a controversial but fascinating theory, posits that life creates the universe rather than the other way around. Just as a musical score sits silent until played, the cosmos might exist in full richness only when perceived. Even Einstein wrestled with this, famously questioning whether the moon exists when no one looks at it. Modern physics offers no definitive answer, but experiments like the delayed choice quantum eraser hint that particles can decide their past behavior based on future observations, a cosmic melody rewriting its own sheet music retroactively. Yet the most profound question remains: why? If consciousness shapes reality, is it by accident or design? Some theorists suggest that self-aware beings are the universe's way of comprehending itself, that the cosmos, in all its majesty, longs to be known. Others argue it's simply how information organizes in complex systems with no deeper meaning. Regardless, the mere possibility transforms our place in the symphony. We're not just listeners, we might be the reason the music plays at all. For decades, we've turned our antennas toward the stars like cosmic eavesdroppers, straining to catch even the faintest whisper of intelligence beyond Earth. The search for extraterrestrial intelligence, SETI, isn't just a scientific endeavor. It's humanity's collective ear pressed against the universe's door, listening for a neighbor's greeting in the dark. Imagine combing through radio static for a pattern so deliberate, so unmistakably artificial, that it could only come from another civilization. That needle in a haystack quest has driven projects like the Allen Telescope Array, which scans thousands of star systems simultaneously, or Breakthrough Listen, analyzing millions of radio channels with supercomputers powerful enough to process years of data in days. Yet what exactly are we listening for? The wow signal, a 72-second burst detected in 1977, remains the closest we've come, a tantalizing blip that matched predictions for an alien transmission but never repeated. Then there's the mysterious fast radio burst FRB 1211, repeating on a 16-day cycle like clockwork, its precise origin still debated. These cosmic oddities tease us with possibilities, but the real prize would be a signal carrying mathematical constants, prime numbers, say, or the hydrogen line frequency, universal languages any advanced civilization might recognize. But radio waves are just one instrument in the cosmic orchestra. SETI now scans for laser pulses, Dyson spheres swallowing starlight, even hypothetical megastructures altering a star's light curve. The discovery of Tabby's star, with its bizarre, irregular dimming, sparked speculation about alien engineering, though dust clouds proved the more likely culprit. Meanwhile, projects like METI flip the script, actively broadcasting messages to nearby stars like a child shouting into a canyon, hoping for an echo. The silence so far isn't necessarily ominous. Space is vast, and civilizations might communicate on timescales spanning centuries. Or perhaps they've moved beyond radio to technologies we can't yet detect, like neutrino communication or quantum networks. Others posit a zoo hypothesis that advanced species intentionally avoid contact, preserving our cultural development like a cosmic nature reserve. What's certain is this: a single confirmed signal would rewrite humanity's place in the symphony. Not as soloists, but as members of a chorus spanning galaxies. Until then, we keep listening, because in a universe this vast, the most profound discovery might be just one frequency away. The Drake equation isn't just a formula, it's a cosmic census, a way to quantify the unquantifiable. Written in 1961 by astronomer Frank Drake, this deceptively simple string of variables tries to answer humanity's oldest question: are we alone in the Milky Way? At first glance, it looks like any other equation with its neat multiplication of factors, but each variable holds a universe of uncertainty, a doorway into debates about star formation, planetary chemistry, and the sheer stubbornness of life itself. Start with the basics. How many stars are born each year in our galaxy? Current estimates suggest around 7, not 7 million or 7,000, just 7. Yet even this seemingly straightforward number hides complexity. Most newborn stars are small, dim red dwarfs, while rare giants like Sirius blaze bright but die young. The equation's next factor, the fraction of stars with planets, was pure speculation when Drake first wrote it. Today, thanks to telescopes like Kepler, we know planets outnumber stars, with billions potentially orbiting in habitable zones. Then comes the real mystery. On how many of those worlds could life actually take root? Earth's biosphere thrives in a delicate balance of temperature, chemistry, and stability, but extremophiles organisms thriving in boiling vents or Antarctic ice hint that life might be more adaptable than we think. Europa's hidden ocean or Enceladus's salty plumes could harbor microbes right in our solar system, rewriting our definition of habitable. But life isn't enough. The equation seeks intelligence. Here, the variables grow murkier. How often does simple life evolve into complex, tool-using civilizations? Earth's timeline offers one data point. Single-celled organisms dominated for billions of years before multicellular life exploded in the Cambrian. And intelligence, that's even rarer. Dinosaurs ruled for over 160 million years without inventing radio telescopes. The final factors are the most haunting. How long do civilizations last? A technological species might flourish for millennia or snuff itself out in centuries. Radio signals from Earth have only leaked into space for about 100 years, a blink in cosmic time. If civilizations are ephemeral, the galaxy might be full of silent ruins, their songs faded to static. Plugging in optimistic numbers, the Drake equation suggests thousands of communicative civilizations could dot the Milky Way. Pessimistic estimates, we might be the only one. The truth likely lies somewhere in between a sparse chorus of voices separated by vast stretches of space and time. Yet, even if the galaxy teems with life, the distances between stars might render the symphony forever out of sync, each note arriving too late to ever harmonize. What makes the Drake equation profound isn't its answers, it's the questions it forces us to confront. Every exoplanet discovered, every extremophile studied, every radio silence passed refines our variables, turning speculation into science. And perhaps that's the point. The equation isn't a calculator but a mirror, reflecting how much we've learned and how much we've yet to hear. There's a moment in every civilization's story when the music could stop, when the symphony of progress hits a note so dissonant, so insurmountable, that the entire composition falls silent. This is the chilling premise of the Great Filter, a concept that might explain why the cosmos seems so eerily devoid of other voices. The theory is simple yet terrifying. Some unknown, catastrophic barrier stands between simple life and interstellar civilization, a hurdle so immense that almost no species clears it. The question isn't just whether the filter exists, it's whether we've already passed it, or if it's still lurking somewhere in our future, waiting to silence us too. Consider the universe's staggering scale. With billions of Earth-like planets in our galaxy alone, the cosmic chorus should be deafening, yet our radio telescopes hear only static. One explanation is that life routinely emerges, only to be snuffed out before it can announce itself to the stars. The filter could be behind us, a bottleneck so narrow that surviving it makes humanity extraordinarily rare. Maybe DNA's leap from simple chemistry to self-replicating life was a fluke so improbable. It's only happened once in our galactic neighborhood. or perhaps the transition from single-celled organisms to complex life required such precise planetary conditions that Earth is a cosmic lottery winner. If so, we've already beaten the odds, and the silence around us is the sound of empty stadiums where no other players qualified. But what if the filter lies ahead? The same technologies that propel civilizations' nuclear power, artificial intelligence, bioengineering could become their undoing. A single war with atom-splitting weapons, a runaway climate collapse, or an AI that outpaces our control might be the universe's way of culling civilizations before they grow too loud. The filter wouldn't need to be inevitable, just statistically likely over billions of years and countless worlds. Even something as mundane as resource depletion could doom species to stagnation, forever trapped on their home planets as their energy demands outstrip supply. The ruins of Easter Island stand as a haunting earthly parable, a society that thrived until it didn't, its people vanishing beneath the weight of their own unchecked consumption. Yet there's a third, more unsettling possibility. The filter isn't a single event but a gauntlet. Survival might require navigating not one catastrophe but dozens, each more improbable than the last. Passing the filter of abiogenesis only to face the filter of industrialization, then the filter of environmental collapse, then the filter of technological autocracy. In this view, civilizations aren't eliminated by one mistake, but by the cumulative weight of their own complexity, like a symphony growing so elaborate it collapses under its own dissonance. The Great Filter isn't just a theory, it's a mirror. If we've already passed it, our responsibility is profound. We might be the universe's best shot at hearing its own melody, the lone singers in a cosmic void. But if the filter still looms ahead, every choice we make, from curbing climate change to governing AI becomes a rehearsal for the performance that decides whether our song continues or fades into the silence. The universe's quiet might not be emptiness. It might be the echo of countless civilizations that never made it to the chorus. What if civilizations could grow so advanced that they didn't just listen to the cosmic symphony, they began conducting it? That's the bold vision behind the Kardashev scale, a method of ranking civilizations based on how much energy they harness. At the lowest level, Type 1 civilizations master their home planet's resources. Think global energy grids, climate control, even weather manipulation. Type 2 civilizations graduate to stellar engineers, capturing the full output of their star, perhaps by building hypothetical megastructures like Dyson spheres. And Type 3, they'd command the energy of an entire galaxy, wielding power so vast, it's indistinguishable from the forces that shape the universe itself. Right now, humanity barely registers on this scale. We're somewhere around Type 0.7, still tethered to fossil fuels and solar panels. But the leap to Type 1 wouldn't just mean more energy, it would redefine our role in the cosmos. Picture a civilization that stabilizes earthquakes, redirects hurricanes, and reforests continents at will. A species no longer at the mercy of its planet, but a caretaker actively tuning its environment like an instrument. The energy demands would be staggering, but so would the creative potential. With that much power, we might sculpt mountains into art, engineer new ecosystems, or even extend Earth's habitable lifespan by millennia. Reaching Type 2 would mean stepping onto the stellar stage, a Dyson sphere, a swarm of orbiting solar collectors enveloping a star, isn't just sci-fi, it's a logical endpoint for any energy-hungry civilization. Imagine harnessing every photon our sun emits, not just the fraction that brushes past Earth. Suddenly, interstellar travel becomes feasible, with energy to accelerate ships to relativistic speeds or power lasers that propel probes to nearby stars. But the real marvel, a Type 2 civilization wouldn't just use its star, it might optimize it. Advanced species could tweak a star's fusion processes, prolonging its life or triggering controlled supernovas to forge heavy elements on demand. They wouldn't just live in the symphony, they'd rewrite the score. The leap to Type 3 is harder to fathom. A galaxy-spanning civilization wouldn't just consume energy, it would choreograph it. Think of manipulating supermassive black holes as gravitational batteries, or weaving dark matter into structures that bend spacetime itself. Some theories suggest such civilizations might leave detectable signatures, entire galaxies dimmed by Dyson swarms, or stars vanishing into artificial wormholes. Others propose even wilder possibilities, engineering universes in labs or escaping entropies grasped by creating pocket dimensions where time flows differently. Yet the Kardashev scale isn't just about raw power. It's about responsibility. Harnessing a star's energy means controlling forces that could vaporize planets. Reshaping galaxies risks unintended consequences for cosmic evolution. The difference between a civilization that plays the symphony and one that shatters it might come down to wisdom, not wattage. So where does that leave us? For now, we're still in the audience, marveling at the universe's grandeur. But one day, if we master energy without self-destructing, we might join the performance, not just as listeners but as composers. The music is waiting. The question is whether we'll learn to play it. Every symphony must end, even the universe's. Picture a piano left untuned for so long that its strings rust, its hammers crumble, and the last echoes of its music fade into silence. That's the fate awaiting our cosmos, not with a bang, but with a whisper so faint it defies comprehension. Scientists call it heat death, the point where entropy wins its billion-year battle, leaving the universe a vast, dark graveyard of scattered particles too sparse and cold to ignite even a single new star. No more galaxies spinning, no more stars burning, just an endless sea of near-absolute zero stillness stretching into eternity. This isn't some distant sci-fi nightmare. It's the inescapable conclusion of thermodynamics. Every process we know, from the fusion in stars to the firing of neurons in your brain, relies on energy gradients, areas of high and low concentration that allow work to be done. But as entropy increases, those gradients level out like a battery draining. Stars exhaust their fuel, black holes evaporate via Hawking radiation, and even the protons that make up atoms might decay over trillions upon trillions of years. The universe, once a roaring fire of creation, becomes embers, then ash, then nothing but a faint infrared glow lingering just above absolute zero. Yet there's a strange beauty in this inevitability. Heat death isn't chaos, it's the ultimate equilibrium, a state of perfect but lifeless balance. Imagine an orchestra where every instrument has played its final note, the musicians frozen in place, the audience departed. The silence isn't random, it's the logical endpoint of every possible vibration having run its course. In a way, heat death is the universe's most composed moment, where every particle has settled into its rightful place, no longer able to clash or create. But here's the twist, this grim finale might not be absolute. Some theories suggest quantum fluctuations could spawn new universes in the void, like bubbles forming in an infinite sea. Others propose that consciousness itself might find ways to persist, harnessing the last trickles of energy to sustain thought in a cosmos where time has lost all meaning. And if civilizations advance far enough, they might cheat entropy entirely, engineering pockets of order in the chaos or escaping into alternate dimensions where the music still plays. For now, though, heat death remains the ultimate deadline, a reminder that the universe's symphony, no matter how grand, is finite. Every star born, every planet formed, every life that arises is a fleeting note in a composition that will one day fall silent. But perhaps that's what makes the music so precious. The universe isn't just playing, It's improvising, creating, and burning bright against the darkness, knowing that every note, no matter how small, matters before the final rest. What if the universe's grand finale isn't an ending at all, but an intermission? The idea of a cyclic cosmology turns the heat-death scenario on its head, suggesting that the universe might not fade into silence but instead reset, like a symphony looping back to its opening movement. Imagine a cosmic pendulum swinging between expansion and collapse, where each big bang is followed by a big crunch, only to rebound into a new creation. This isn't just poetic speculation. It's a serious theory backed by equations, one that paints the cosmos as an eternal performer, rehearsing the same composition across infinite time. The math behind cyclic models hinges on dark energy's behavior. If the force driving the universe's accelerated expansion weakens over time, gravity could eventually gain the upper hand, pulling everything back together in a reversal of the Big Bang. Space would contract, temperatures would soar, and all matter might dissolve into a primordial soup, only for another explosion to birth a fresh universe, nearly identical to the last. In this view, the cosmic microwave background isn't just an echo of our universe's birth but a fingerprint left by countless cycles before it, each iteration subtly tweaking the constants of physics like a musician adjusting their instrument between sets. But how would these cycles leave traces? Some theorists propose that colliding universes in a higher dimensional, bulk space could imprint patterns in the cosmic microwave background, wrinkles in spacetime acting as scars from past collisions. Others suggest that black holes, those cosmic vaults of information, might preserve data across cycles, encoding the history of one universe into the structure of the next. It's a haunting thought. The galaxies we see tonight might be phantoms of an earlier version of reality, their light echoing across eternity. Yet cyclic cosmology faces challenges. The second law of thermodynamics insists entropy always increases, meaning each cycle should start with more chaos than the last. Over infinite iterations, the universe would grow ever more disordered, like a recording degrading with each replay. Some models attempt to sidestep this by invoking a cosmic reset during the contraction phase, where entropy is somehow wiped clean, but the mechanics remain speculative, dancing at the edge of known physics. The most profound implication: if cycles are real, time itself becomes an illusion. There's no true beginning or end, just an endless rhythm of creation and dissolution. Civilizations might rise and fall in each iteration, never knowing their atoms once belonged to other stars, other worlds, other versions of themselves. The symphony isn't just repeating, it's improvising, with each cycle adding new variations to an infinite score. Whether the universe is a one-time performance or an eternal encore remains one of cosmology's great mysteries. But the mere possibility invites us to reconsider our place in the cosmos, not as fleeting spectators, but as participants in a melody that might never truly end. Dark energy is the universe's most enigmatic soloist, an invisible performer speeding up the cosmic symphony in ways no one saw coming. For decades, astronomers assumed gravity would eventually slow the expansion of the universe, pulling galaxies back together in a grand finale. But in the late 1990s, observations of distant supernovae revealed something astonishing. The universe isn't just expanding, it's accelerating. Some mysterious force, now called dark energy, is stretching space itself faster and faster, like a conductor urging the orchestra to play at an ever-quickening tempo. What makes dark energy so baffling is its sheer dominance. It accounts for nearly 70% of the universe's total energy content, dwarfing everything else: stars, galaxies, even dark matter. Yet we can't see it, trap it, or even fully define it. the leading theory suggests dark energy might be the energy of empty space itself, a property Einstein once called the cosmological constant, a term he later dismissed as his greatest blunder. But the universe, it seems, had other plans. If this vacuum energy is real, it means every cubic centimeter of space, no matter how empty, hums with an invisible push, a kind of anti-gravity driving galaxies apart. The consequences are staggering. As dark energy accelerates the universe's expansion, distant galaxies will eventually recede so fast their light can never reach us. Future civilizations might gaze at a night sky nearly empty of stars, their own galaxy an isolated island in an ever-darkening void. Galaxy clusters once bound by gravity will be torn apart, their stars scattered like notes lost in the wind. Even time itself could become meaningless in a cosmos so vast and diluted that no new events ever occur, a heat death not from cold but from infinite dilution. Yet dark energy isn't just a force of destruction. Without it, the universe might have collapsed in on itself eons ago, snuffing out any chance for life to emerge. Its delicate balance with gravity created the perfect conditions for galaxies to form and stars to ignite. In a way, dark energy is both the composer and the disruptor, setting the stage for existence while ensuring the performance won't last forever. The biggest mystery, dark energy's strength seems unnervingly fine-tuned. If it were slightly stronger, the universe would have ripped apart before atoms could form. Slightly weaker, and gravity would have crushed everything into a black hole. This precision has led some to wonder, is dark energy a constant, or could it evolve over time? Could it one day weaken, reverse, or even trigger a catastrophic big rip that tears atoms apart? For now, dark energy remains a cosmic riddle, its true nature hidden in the fabric of space. But every new telescope, every deeper map of the universe's expansion, brings us closer to understanding this invisible maestro, the force that's not just shaping the universe's destiny, but rewriting its finale in real time. What if everything we see, the stars, the galaxies, even the space between them, is nothing more than an illusion, a cosmic trick of the light? That's the radical proposition of the holographic principle, a theory so strange it sounds like science fiction. Imagine attending a concert where the music seems to surround you, filling the air with sound, only to discover the entire symphony was actually encoded on a flat vinyl record all along. The holographic principle suggests our three-dimensional universe might work the same way, a breathtakingly realistic projection of information stored on a distant, two-dimensional surface. This isn't just philosophical musing, it comes straight from the math of black holes. When physicists calculated how much information a black hole can hold, they hit a startling realization. The maximum data it can store isn't determined by its volume, but by its surface area. It's as if every particle, every force inside the black hole was somehow written on its event horizon, like grooves on a record. Take this idea further, and the entire universe might operate the same way. The galaxies we see, the planets we walk on, even our own thoughts could be shadows cast by data etched onto some unimaginably vast boundary at the edge of reality. Think of it like a hologram sticker. Shine light through it and a three-dimensional image appears floating in midair. The sticker itself is flat, but the image it creates has depth, texture, even motion. Now scale that up to cosmic proportions. The equations suggest that all the information needed to describe our universe, every star, every atom, every vibration of every string in string theory, might fit onto a surface at the universe's edge. We're not just in the universe, we might be its holographic playback. But how could this possibly work? One clue comes from quantum entanglement, that eerie phenomenon where particles instantly influence each other across vast distances. It's as if they're not separate entities but projections of a deeper, interconnected code, like two instruments in an orchestra playing from the same sheet music, even if they're on opposite sides of the stage. The holographic principle takes this further, proposing that entanglement isn't just a quirk of quantum mechanics, but the glue holding reality's illusion together. The implications are dizzying. If the universe is a hologram, then time and space aren't fundamental, they're emergent properties, like the melody that arises from individual notes. Gravity, the force that shapes galaxies, might not be a force at all but a side effect of information processing on that distant boundary. Even our perception of free will could be reshaped, with every choice we make already encoded in the cosmic data. Yet for all its elegance, the holographic principle remains fiercely debated. Can a flat surface really encode the richness of a supernova, the complexity of a human brain, the vastness of a galaxy cluster? Some physicists argue that while the math works for black holes, scaling it to the entire universe is a leap too far. Others point out that if the universe is a hologram, we should be able to detect pixelation, tiny, fundamental units of space-time graininess in high-energy physics experiments. So far, no such pixels have been found. Whether the holographic principle holds up or not, it forces us to confront a profound possibility. Reality might be far stranger, far more interconnected than we ever imagined. The universe's symphony isn't just playing around us, it might be playing us, every note, every vibration, a fleeting projection of some deeper, hidden harmony. The next time you look up at the stars, ask yourself, are we the music or just the echo? At the heart of every instrument, from the deepest cello to the highest violin, lies a simple truth: vibration creates music. Now imagine that same principle, but applied to the very fabric of reality. String theory suggests that every particle in the universe, from the photons carrying light to the quarks inside atoms, isn't a point but an unimaginably tiny, vibrating string. These strings aren't made of anything smaller. They're the universe's fundamental notes, each vibration pattern producing a different particle-like variations in a melody. An electron might be a string humming at one frequency while a quark sings at another. Even gravity, the grand conductor of the cosmos, emerges from these microscopic harmonies. A radical idea that could finally unite quantum mechanics and general relativity, the two great but conflicting theories of modern physics. Think of these strings as the universe's smallest possible guitar strings. Just as plucking a guitar string produces different notes depending on tension and length, these cosmic strings vibrate in distinct ways based on their energy and dimensions. But here's the twist: while a guitar string exists in 3 dimensions, these theoretical strings vibrate in at least 10/6 of which are curled up so tightly, we'll never perceive them directly. It's as if every particle we see is just the shadow of a richer, multidimensional symphony playing out in realms beyond our senses. String theory's elegance lies in its unity. In traditional physics, particles are like a scattered orchestra. Electrons obey quantum rules. Gravity follows Einstein's equations, and never the twain shall meet. But strings offer a single framework where all forces and particles arise from the same basic ingredient. A graviton, the hypothetical particle carrying gravity, isn't an outsider. It's just another vibrational state, like a low bass note in the string's repertoire. Even the bizarre quantum behavior of particles makes sense if they're not static dots but dynamic, oscillating filaments. Yet the theory isn't without discordant notes. For one, those extra dimensions aren't just hidden, they're mathematically necessary but physically untestable with current technology. And then there's the landscape problem. String theory allows for perhaps 10 to the power of 500 possible configurations, each representing a universe with different physical laws. Are we just one cosmic tune in an infinite multiverse of melodies? Critics argue this makes the theory unfalsifiable, more philosophy than science. Supporters counter that it's a work in progress after all. Relativity and quantum mechanics once seemed equally outlandish before evidence caught up. The most poetic implication: if strings are real, the universe isn't just governed by mathematics, it is mathematics. Every collision of particles, every warp in space-time, every flicker of starlight could be the physical manifestation of abstract vibrational equations. We're not just listeners to the cosmic symphony, we're expressions of its deepest rhythms, temporary harmonies in an eternal song. Whether string theory ultimately holds the key to reality's composition or fades into the annals of beautiful but unproven ideas, it reminds us that the universe might not just have music, it might be music, written in vibrations too small to hear but too profound to ignore. What if the grand cosmic symphony we've been marveling at isn't a natural phenomenon at all, but an artificial composition, meticulously coded by beings so advanced, their reality makes ours look like a rudimentary program? This is the simulation hypothesis, a theory that suggests our universe, with all its galaxies, black holes, and quantum quirks, might be nothing more than an elaborate simulation running on some unfathomable computer. At first glance, it sounds like the plot of a sci-fi movie, but some of the brightest minds in physics and philosophy take it seriously. The idea hinges on a simple thought experiment. If civilizations eventually develop the power to create hyper-realistic simulations of conscious beings, the number of simulated minds would vastly outnumber the original ones. Statistically speaking, the odds with a base reality could be vanishingly small. But how would we even begin to test such a radical claim? One approach looks for potential glitches in the matrix, tiny anomalies in the fabric of reality that might hint at underlying code. For instance, quantum mechanics already behaves in ways that feel eerily digital. Particles exist in multiple states until observed, as if the universe is optimizing processing power by only rendering what's being watched. Even the speed of light, the universe's ultimate processing limit, could be seen as a built-in constraint to prevent system overload. Some theorists point to mathematical constants like pi or the fine structure constant as possible hard-coded parameters, fine-tuned to keep the simulation stable. Then there's the argument from complexity. The universe operates on mathematical laws so precise they can predict the spin of an electron or the orbit of a planet with staggering accuracy. Could this mathematical elegance be evidence of deliberate design? Or is it just the way any self-consistent simulation would need to function? Skeptics counter that invoking simulators doesn't solve the problem of origins, it just kicks the can down the road. Who created the simulators, and what about their creators? The chain of explanations could stretch infinitely, leaving us no closer to ultimate truth. Yet the simulation hypothesis isn't just philosophical speculation. Some scientists have proposed empirical tests, like searching for pixelation in high-energy particle collisions or anomalies in cosmic rays that might reveal the universe's resolution limit. Others suggest that if our reality is a simulation, it might contain compressed or simplified physics in distant, unobserved regions, like a video game reducing detail in areas the player isn't viewing. Even our dreams, with their fluid, illogical landscapes, could be seen as miniature, low-budget simulations running on the wetware of our brains. The ethical implications are just as dizzying. If we're simulations, do our lives have intrinsic meaning, or are we mere data points in some higher being's experiment? Some argue it changes nothing. Our experiences feel real to us, and that's what matters. Others worry it could undermine morality, reducing empathy to lines of code. But here's a twist. if we one day create conscious simulations ourselves, we'd become the gods of their universe, forced to grapple with the same questions. Whether the symphony is composed by nature or by programmers, the music still plays, the stars still shine, the galaxies still spin, and the mysteries still beckon. Perhaps the real question isn't whether we're in a simulation, but what we choose to do with the reality we perceive. After all, even if this is all code, the beauty, the wonder, and the hunger to understand feel undeniably real. And in that sense, the music, artificial or not, is no less breathtaking. Chaos isn't just randomness, it's the universe's way of composing improvisational jazz. At first glance, the cosmos seems governed by strict, predictable laws. Planets follow orbital paths, stars burn at calculable rates, and galaxies spin with mathematical precision. But beneath this orderly surface lies a wild undercurrent, where tiny, imperceptible shifts can spiral into cosmic upheavals. This is chaos theory in action, the idea that even in a deterministic universe, the slightest variation in initial conditions can lead to dramatically different outcomes. Think of it like a single misplaced note in a symphony that cascades into an entirely new melody, reshaping the performance in ways no conductor could anticipate. Take our own solar system. For centuries, astronomers assumed the orbits of planets were as stable as clockwork, a celestial dance set in stone by Newton's laws. But modern simulations reveal a startling truth. Over millions of years, gravitational nudges from tiny asteroids or distant stars can accumulate, throwing planetary trajectories into disarray. Mercury, for instance, has a 1 in 50 chance of veering wildly off course in the next 5 billion years, potentially colliding with Venus or plunging into the Sun. These aren't flaws in the universe's design, they're features, reminders that predictability has its limits, even in the void of space. Now scale that up to galaxy formation. In the early universe, quantum fluctuations smaller than atoms' random blips in density grew under gravity's pull to become the seeds of galaxies. Those microscopic irregularities determined whether a region of space would birth a sprawling spiral like the Milky Way or a dense elliptical galaxy. The same principle applies to star clusters, where the gravitational pull of a single rogue star can scatter hundreds of others, rewriting the structure of an entire stellar nursery. Chaos doesn't just disrupt, it creates, sculpting the universe's large-scale structure through a series of unpredictable, snowballing events. Even the cosmos's most violent phenomena dance to chaos's tune. Supernovas, those brilliant stellar explosions, are triggered by instabilities deep within a star's core, turbulent convection currents, and nuclear reactions so sensitive that a fractional change in temperature or pressure can accelerate a star's demise by millennia. The Crab Nebula, the remnant of a supernova observed in 1054, owes its intricate, swirling filaments to chaotic magnetic fields and shockwaves that twisted its debris into fractal patterns no human artist could replicate. But here's the twist: chaos isn't the opposite of order, it's the engine of complexity. Without it, the universe might have settled into a bland, uniform soup of particles. Instead, chaos weaves intricate tapestries like Jupiter's Great Red Spot, a storm raging for centuries thanks to turbulent atmospheric dynamics, or the fractal branching of cosmic webs that connect galaxy clusters across billions of light years. These structures aren't mistakes in the symphony, they're proof that the universe thrives on controlled dissonance, blending predictability and surprise into something greater than the sum of its parts. So while we map the cosmos with equations and models, chaos reminds us that some things will always elude our grasp, not because we lack knowledge, but because the universe itself thrives on spontaneity. The next time you gaze at the night sky, remember, Those stars aren't just following a script, they're improvising, their paths shaped by countless invisible nudges, their stories written in the language of uncertainty. And in that unpredictability lies the universe's most breathtaking creativity. Not too hot, not too cold, but just right. Earth didn't just stumble into the perfect spot for life by accident. Our planet orbits the Sun in a celestial sweet spot known as the habitable zone, where temperatures allow water to exist as a liquid, not just ice or vapor. This delicate balance isn't luck, it's physics conducting a symphony of conditions so precise, even slight variations would silence life's melody entirely. Picture a singer hitting a note so perfectly, it resonates through a concert hall. Earth's position in the solar system is that note, a rare harmony of distance, atmosphere, and stellar energy that transforms a rocky world into a cradle of biology. But the habitable zone isn't just about location. Venus and Mars technically orbit within our Sun's Goldilocks range, yet one is a scorching greenhouse and the other a frozen desert. What sets Earth apart is a chorus of finely tuned factors. Our planet's size generates enough gravity to hold an atmosphere, but not so much that it crushes geological activity. A molten iron core fuels a magnetic field, deflecting lethal solar winds like an invisible shield. Even the Moon plays a role. Its gravitational tug stabilizes Earth's tilt, preventing wild climate swings that would turn seasons into catastrophes. Together, these elements create a stability rare in the cosmos, allowing life to evolve across billions of years without interruption. The symphony gets richer when you consider stellar chemistry. Stars like our Sun, G-type main sequence stars, offer a rare blend of longevity and calm. Massive stars burn too hot and die too young, showering their planets with lethal radiation before life can take hold. Tiny red dwarfs, though abundant, often bombard their planets with flares that strip away atmospheres. The Sun, by contrast, provides steady energy for over 10 billion years, a marathon performance that gave life the time it needed to progress from single-celled organisms to civilizations. Then there's the galactic neighborhood, too close to the Milky Way's crowded center, and Earth would face constant supernova explosions and gravitational chaos. Too far out in the sparse outskirts, and the planet might lack heavy elements like iron and carbon, the building blocks of life. Our solar system orbits in a quiet suburban spiral arm, close enough to resources but far enough from cosmic hazards. Even Jupiter acts as a guardian, its massive gravity deflecting asteroids that might otherwise pummel Earth into sterility. The miracle isn't just that these conditions exist, it's that they persist. Plate tectonics recycle carbon, regulating temperatures across eons. The water cycle distributes heat and nutrients, while photosynthesis turns sunlight into stored energy, fueling ecosystems. Each component interlocks like instruments in an orchestra, no single section overpowering the others. And just as a symphony needs silence between notes, Earth's history includes mass extinctions reset buttons that allowed new life forms to emerge and adapt. Yet the Goldilocks Principle extends beyond our planet. Astronomers have discovered thousands of exoplanets in their own habitable zones, some with ingredients like water vapor and organic molecules. But none, so far, replicate Earth's full ensemble of life-supporting traits. That doesn't mean they're silent, only that the universe's symphony is vast, with movements we've yet to hear. For now, Earth remains the only proven crescendo in a cosmos still tuning its instruments. And that makes our world not just a rarity, but a revelation proof that against staggering odds, the universe can compose not just stars and planets, but the conditions for a song as complex as life itself. Humanity has spent millennia gazing at the stars, first with wonder, then with telescopes, and now with rovers and probes. But we stand on the brink of something far grander, the moment when our species transitions from passive observers to active participants in the universe's symphony. The next era of space exploration won't just be about discovery. It will be about creation, reshaping worlds, harnessing cosmic forces, and perhaps even composing new harmonies in the grand celestial score. Imagine a future where we don't just study asteroids, but redirect them to mine precious metals, where we don't merely observe Mars, but terraform its rusty plains into lush biospheres. Where our spacecraft don't just orbit distant exoplanets, but seed them with the building blocks of life. This isn't science fiction. It's the inevitable next movement in humanity's journey, one where we shift from reading the music to writing it. Consider the transformative power of asteroid mining. These rocky remnants from the solar system's birth contain platinum, gold, and rare earth metals in quantities that dwarf Earth's reserves. Companies like Planetary Resources and Deep Space Industries are already developing robotic prospectors to survey and extract these materials. But the real revolution begins when we move beyond extraction to engineering using asteroids as raw material for orbital megastructures. Picture vast solar power stations beaming clean energy to Earth, or rotating space habitats built from the nickel-iron bones of captured asteroids. Suddenly, humanity isn't just a consumer of cosmic resources. We're a sculptor of them, rearranging matter on a planetary scale. Then there's the dream of terraforming. Mars, with its frozen water and thin atmosphere, is the most promising canvas for planetary-scale artistry. Early steps might involve pumping greenhouse gases into the Martian air to trigger a warming cascade, or deploying algae engineered to survive the harsh environment and slowly convert carbon dioxide into breathable oxygen. Over centuries, these efforts could thicken the atmosphere, melt subsurface ice into rivers, and raise temperatures enough for liquid water to flow. The red planet would transition from a barren wasteland to a living world, a second movement in Earth's biosphere symphony. Critics argue the ethics of altering another planet, but proponents counter that life itself is a force of transformation, and spreading it may be our highest cosmic calling. But our role in the symphony could extend beyond our solar system. Breakthrough Starshot, a project to send gram-scale probes to Alpha Centauri at 20% light speed, hints at a future where humanity's presence isn't limited by biology. These nanocraft, propelled by powerful lasers, could carry microbial life or encoded DNA sequences, seeding distant worlds with the potential for evolution. It's a provocative idea that we might become the gardeners of the galaxy, scattering the ingredients of life like cosmic Johnny Appleseeds. Some even speculate about von Neumann probes, self-replicating machines that could explore and build infrastructure across star systems, effectively making humanity a multi-stellar species without boarding a single ship. Yet with this power comes profound responsibility. The same technologies that let us heal planets could also destroy them, strip mining moons, destabilizing orbits, or accidentally contaminating pristine ecosystems with earthly microbes. The universe's symphony has played for billions of years without our input. Our newfound ability to alter its score demands wisdom as much as ambition. Perhaps that's the ultimate test awaiting us among the stars, not whether we can conquer space, but whether we can harmonize with it, the most thrilling possibility. That humanity's greatest contribution to the cosmic symphony might still be unknown. Just as medieval peasants couldn't have imagined satellites or gene editing, we likely can't foresee the full scope of our interstellar potential. Maybe we'll discover ways to harness dark energy, communicate through quantum entanglement, or even manipulate space-time itself. Whatever the future holds, one thing is certain: the universe's music isn't finished. And for the first time in 13.8 billion years, one of its listeners is learning to play along. We're standing at a crossroads unlike any in human history, not just as explorers of the cosmos, but as potential shapers of it. With the ability to deflect asteroids, terraform planets, or even engineer stars looming on the horizon, we face a profound ethical dilemma. Just because we can alter the universe's grand symphony, should we? This isn't just about capability, it's about responsibility. Imagine a future where we nudge a killer asteroid away from Earth, only to send it careening toward another inhabited world we didn't know existed. Or consider the unintended consequences of geoengineering Mars. What if our efforts to create a second Earth accidentally erase unique Martian chemistry that held clues to the origins of life itself? The power to conduct the cosmos comes with risks as vast as space itself. Take the case of planetary protection. Right now, spacecraft bound for Mars undergo rigorous sterilization to avoid contaminating the red planet with earthly microbes. It's a precaution rooted in humility, the recognition that we might not be the only players in this symphony. But what happens when we shift from observation to transformation? Terraforming Mars by introducing greenhouse gases or engineered algae could jumpstart its biosphere, but it might also obliterate native life forms too subtle for our instruments to detect. The same ethical quandary applies to icy moons like Europa, where drilling through its frozen crust to explore the subsurface ocean could introduce earthly bacteria, forever altering an alien ecosystem. Are we stewards or conquerors? The line blurs when we wield planet-sized tools. Then there's the question of cosmic-scale engineering. Projects like Dyson spheres, hypothetical megastructures to harness a star's energy, could power civilizations for millennia, but they'd also be visible across galaxies. Would such a project signal our presence to potentially hostile neighbors? Or worse, could it starve other planets in the system of vital starlight, disrupting their climates in ways we can't foresee? Even seemingly benign acts like redirecting comets to water dry worlds might destabilize orbital dynamics over centuries, triggering collisions we didn't anticipate. The universe is a web of delicate balances, and pulling one thread could unravel harmonies we don't yet understand. But the most unsettling dilemma might be this: what if our interventions silence the symphony altogether? The Fermi paradox suggests that advanced civilizations might self-destruct or be destroyed before they can colonize the stars. Could our tinkering with cosmic forces attract the wrong kind of attention? Or worse, could it reveal that the universe's silence isn't accidental but enforced? Some theories propose the existence of predatory civilizations that eliminate rivals, a dark forest where making noise is fatal. In that scenario, our ambition to conduct the symphony could be the very thing that gets us ejected from the orchestra. Yet there's a counter-argument that not acting is its own ethical failure. If we detect an asteroid on a collision course with Earth a century from now, refusing to deflect it would be unconscionable. If Mars remains barren when we have the tools to awaken it, are we honoring the universe or wasting its potential? The same moral imperative that drives us to heal ecosystems on Earth might compel us to seed life elsewhere, especially if we're alone in the cosmos. After all, a symphony with only one musician is a tragedy. Perhaps the answer lies in a new kind of ethics, one that weighs cosmic consequences alongside human ambition. Just as doctors swear to first do no harm, interstellar engineers might need a similar oath, prioritizing caution over haste and collaboration over dominance. The universe has composed its melody for billions of years without us. Our role shouldn't be to drown it out, but to listen deeply before joining in. Because the greatest honor isn't conducting the symphony, it's being invited to play. The most mesmerizing symphonies aren't the ones with every note resolved, they're the ones that leave you leaning forward, aching for the next refrain. The universe understands this better than any composer. Its greatest gift isn't the answers it provides, but the mysteries it refuses to surrender. Think of dark matter's invisible grip, the enigma of consciousness, or the question of what triggered the Big Bang. These aren't gaps in our knowledge, they're invitations, written in starlight and spacetime, urging us to listen deeper. Consider how a black hole's event horizon teases us with paradoxes. According to Einstein, anything crossing it is lost forever, shredded into atoms. Yet quantum mechanics insists information can't be destroyed. Both theories work flawlessly in their own domains until they collide at the edge of a singularity where the rules dissolve into chaos. This isn't a flaw in the cosmic score, it's a deliberate crescendo of contradiction, reminding us that reality's fabric is stranger than our equations can capture. The tension between known and unknown isn't a barrier, it's the engine of discovery. Or take the puzzle of life's origins. We've recreated amino acids in labs, traced the chemistry of primordial Earth, and even found organic molecules on asteroids. But how inert matter crossed the threshold into self-replicating life remains one of science's grandest unsolved melodies. Some researchers propose hydrothermal vents as crucibles. Others point to electric sparks in ancient atmospheres, while wilder theories suggest cosmic seeding by comets. The beauty isn't in choosing one narrative, it's in the harmony of possibilities. Each hypothesis a different instrument playing the same haunting question: are we alone? Even our tools for unraveling the cosmos feed the mystery. Telescopes like James Webb peer back 13 billion years, capturing galaxies too mature to exist so soon after the Big Bang. Each observation should clarify the past, yet these cosmic toddlers, brimming with stars, only deepen the riddle of how structures formed so quickly. It's as if the universe is improvising, tossing curveballs that force us to rewrite the sheet music mid-performance. Perhaps this is why the cosmic symphony never grows stale. The moment we think we've deciphered its patterns, it throws in a syncopated rhythm, like dark energies accelerating expansion, or quantum entanglement's spooky connections across light years. These aren't frustrations to be solved, they're the universe's way of keeping the music alive, ensuring there's always another movement waiting in the wings. So while we map exoplanets and simulate multiverses, the most profound truth may be this: wonder thrives in the unresolved. A universe that handed us all its secrets would be a silent concert hall. But one that whispers just enough to keep us searching, that's a masterpiece in perpetual rehearsal, its final bars forever unwritten. And we're not just the audience, we're the ones who'll help compose what comes next. There's a moment in every great piece of music where science and art collide, where the rigid laws of physics melt into something that stirs the soul. The universe doesn't just obey equations, it inspires sonnets, paintings, and symphonies that echo its grandeur. For centuries, artists have looked to the stars not just for light, but for meaning, translating cosmic wonders into works that resonate deep within us. And scientists, they're artists in their own right, sketching galaxies in data, composing theories with mathematical elegance, and uncovering rhythms in the chaos that feel almost musical. Take the harmonies of the spheres, an ancient idea that planets move in celestial musical intervals. Pythagoras imagined the cosmos as a lyre, its strings vibrating with the perfect ratios of orbital periods. Though we now know planets don't literally sing, modern astronomy reveals a deeper truth. The universe does hum. Pulsars tick like metronomes, gravitational waves ripple space-time like bass notes, and the cosmic microwave background whispers the universe's first chord. Composers like John Cage and Terry Riley have woven these rhythms into avant-garde scores, turning telescopic data into soundscapes that let us hear the cosmos. NASA itself has sonified galaxy clusters, translating X-ray emissions into eerie, resonant tones, proof that science and art share the same lexicon of wonder. Visual artists, too, chase the ineffable. Van Gogh's Starry Night isn't just a painting, it's turbulence physics rendered in swirling brushstrokes, mirroring the same patterns found in distant nebulae. The Hubble Space Telescope's images, colorized to highlight chemical elements, look like abstract expressionist masterpieces, vibrant clouds of hydrogen pink and oxygen blue. And then there's the art of simulation, supercomputer models of colliding galaxies, their dancer-like spirals so breathtaking, they blur the line between calculation and choreography. Poets have long been the universe's translators. Walt Whitman wrote of the vast similitude spanning galaxies and grass blades, while Tracy K. Smith, in her Pulitzer-winning Life on Mars, grapples with the cosmic loneliness of being a speck of light flickering in a distant sky. Even Carl Sagan's Pale Blue Dot, though rooted in science, reads like verse, a meditation on our fragile place in the void. These aren't just embellishments, they're essential acts of interpretation, helping us feel what equations alone can't convey. Perhaps the most profound collaborations happen when scientists and artists work side by side. The Black Hole Sonification Project at MIT turns gravitational waves into audible vibrations, letting us experience a black hole merger as a rising chirp. Installations like Cosmocomics, inspired by Italo Calvino's stories, use VR to immerse viewers in particle collisions or supernova explosions, making the invisible visceral. These projects remind us that curiosity and creativity are twin forces, one dissecting the universe's mechanisms, the other illuminating its soul. So the next time you hear a symphony, remember, those notes are echoes of supernovas. When you stand before a painting, see the brushstrokes of quantum fields. The universe isn't just a subject for art or a puzzle for science. It's the original masterpiece, and we're all trying to translate its beauty in our own way. Whether through a telescope or a violin, the goal is the same: to listen, to understand, and to add our own small, shimmering note to the eternal song. Mathematics isn't just a human invention, it's the universe's native language, the hidden sheet music guiding every cosmic movement. From the spiraling arms of galaxies to the quantum flutter of subatomic particles, the world obeys mathematical laws with a precision that borders on the supernatural. Take Newton's law of gravitation, written in the 17th century, yet still predicting the orbit of Pluto centuries later with pinpoint accuracy. Or Maxwell's equations, which unified electricity and magnetism into a single electromagnetic symphony, long before we could observe its waves rippling through space. These aren't just tools, they're revelations, uncovering a reality where numbers and symbols dance in perfect harmony with the physical world. Consider the way a simple equation, E equals mc squared, unlocked the energy of stars. Einstein's formula didn't just describe nature, it revealed a truth so profound, it reshaped our understanding of matter itself. The same math that predicts the path of a thrown baseball also governs the collapse of a dying star into a black hole, proving that the universe operates on principles scalable from the infinitesimal to the infinite. Even chaos, with its apparent randomness, follows mathematical patterns, fractals repeating in coastlines, cloud formations, and the distribution of galaxies. The cosmos doesn't just tolerate math, it thrives on it, as if every law of physics were a stanza in an eternal poem. But how does math, born from human minds, mirror reality so flawlessly? Some argue it's because we've tailored math to fit what we observe, like a composer writing music to match a dancer's steps. Others propose a more radical idea, that math exists independently, a Platonic realm of perfect forms that the physical universe imperfectly echoes. When physicists discover equations like the Schrödinger wave function, which predicts quantum behavior with eerie accuracy despite no intuitive reason for its form, it feels less like invention and more like eavesdropping on the cosmos's private conversation. The most breathtaking examples lie in the universe's symmetries. The Fibonacci sequence appears in sunflower seeds and spiral galaxies alike. The number pi emerges in river bends and planetary orbits. Even the distribution of prime numbers seems to whisper through the energy levels of atomic nuclei. It's as if the universe is a grand fugue, its themes recurring at every scale, waiting for us to recognize the patterns. Yet for all its power, math has limits. Dark matter and dark energy resist tidy equations, and quantum mechanics' probabilistic nature defies classical determinism. Perhaps the universe's full symphony includes notes we haven't learned to hear, or perhaps, like any great composition, it thrives on the tension between predictability and surprise. Either way, one thing is certain: the deeper we listen, the more the cosmos reveals its genius measure by measure. There's something primal in the way we look up at the night sky, not just to observe, but to connect. For millennia, humans have woven the cosmos into myth and music, mapping constellations onto the unknown as if the stars themselves were notes in a song only we could hear. This isn't just curiosity, it's a longing to find rhythm in the chaos, to feel the universe's pulse and know we're part of its score. Psychologists call this the overview effect, the profound shift astronauts report when seeing Earth from space, a sudden, visceral understanding that borders dissolve in the face of cosmic unity. But you don't need to leave the planet to feel it. Every time we hum along to a song that gives us chills or lose ourselves in the symmetry of a seashell spiral, we're tapping into the same instinct, a hunger for harmony that mirrors the universe's own patterns. Dig deeper, and this craving reveals itself in unexpected places. Ancient cultures from the Maya to the Maori didn't just study the stars, they composed celestial calendars, aligning pyramids and navigation routes with celestial events, as if building earthly echoes of heavenly order. Even modern science, for all its rigor, dances with aesthetics. When Kepler discovered planets moved in ellipses, not perfect circles, he didn't just record data. He wrote of hearing the harmony of the spheres, a music so divine it brought him to tears. Einstein, too, spoke of his theories as melodies waiting to be plucked from the cosmos. These aren't poetic flourishes, they're clues to how deeply wired we are to seek resonance between our inner worlds and the outer universe. But why? Evolutionary biologists suggest this impulse might be rooted in survival. Recognizing patterns, whether in the changing seasons or the predictable rise of Sirius, helped our ancestors thrive. Yet that doesn't explain the awe that follows, the way a Hubble image of the pillars of creation can stir something beyond utility. Philosophers argue it's because we're made of stardust, literally, the carbon in our bones, the iron in our blood, forged in stellar furnaces billions of years ago. When we gaze at the cosmos, we're not just observers, we're fragments of it remembering itself. The music we hear in planetary orbits or quantum vibrations isn't metaphor, it's genealogy. This longing for cosmic harmony also reflects our deepest existential questions. If the universe operates by elegant, universal laws, does that mean our lives, too, have an underlying order? Religions have long answered yes, framing creation as a divine symphony with humanity in the chorus. Secular perspectives find solace in the opposite, that amid the chaos, we create meaning by composing our own melodies. Both views share a core truth: the universe's music isn't just out there. It's a mirror reflecting back whatever we most need to believe about our place in the grand arrangement. Perhaps that's why the silent vastness of space unnerves us as much as it inspires. The idea that the cosmos might be indifferent to our symphonies is unsettling. But there's another way to see it. The universe doesn't need to care for the music to matter. A falling tree makes sound waves whether anyone hears them or not. The beauty lies in our ability to listen, to translate light into art, gravity into song, and in doing so, weave ourselves into the fabric of something infinitely larger. The cosmic symphony doesn't demand our participation, but it plays all the same, and we're richer for adding our voices. Every discovery we make about the cosmos, every distant galaxy mapped, every exoplanet catalogued, every quantum mystery unraveled, is more than data. It's a story we're telling future generations, a message in a bottle tossed into the ocean of time. Think of the ancient astronomers who first charted the stars without telescopes, their observations etched into clay tablets and parchment. Those early star catalogues weren't just scientific records. They were humanity's first love letters to the universe, fragile threads connecting us to minds that gazed at the same constellations millennia ago. Today, our tools are spacecraft and supercomputers, but the impulse remains the same: to leave behind breadcrumbs of understanding for those who'll come after us. Consider the golden record aboard Voyager, a literal time capsule carrying greetings in 55 languages, the sounds of Earth's oceans, and even the brainwaves of a person in love. It wasn't designed just for extraterrestrials. It was a mirror held up to ourselves, a snapshot of who we were in the late 20th century. Centuries from now, long after our cities have turned to dust, that record will still be drifting among the stars, a testament to a species that dreamed loudly enough to be heard across the light years. The same goes for the James Webb Space Telescope's deep field images or the gravitational wave detections in LIGO archives. These aren't just breakthroughs, they're cultural heirlooms, proof that we lived in an era when the universe began whispering its secrets back to us. Yet legacy isn't just about preservation, it's about responsibility. The radio signals leaking from Earth since the 1930s now form a bubble 80 light-years wide, broadcasting everything from Churchill's speeches to sitcom laugh tracks into the void. Future civilizations, human or otherwise, might sift through this noise like archaeologists piecing together pottery shards. What will they conclude about us? That we were curious, reckless, hopeful. Every satellite we launch, every probe we land, even the debris we leave in orbit becomes part of that narrative. The scars on Mars from rover wheels, the footprints on the moon, these are more than engineering feats. They're indelible lines in a story we're co-writing with the cosmos itself. And then there's the knowledge we're passing forward. The equations scribbled by Einstein, the algorithms training AI to find exoplanets, the genetic codes of Earth species stored in lunar arcs. These are the real inheritance we're building. When a child today learns that black holes warp spacetime or that DNA might exist on Enceladus, they're not just absorbing facts. They're inheriting a tradition of wonder, a baton passed from Galileo to Hubble to the next generation holding makeshift telescopes in their backyards. The most profound legacy isn't the answers we've found, but the questions we've taught others to ask. Perhaps the greatest story we're telling is one we can't yet read, the one written in the future tense. If humanity someday spreads to the stars, our descendants will look back at this era as their origin myth, the chapter where their ancestors first reached beyond the cradle. And if we don't, if climate change or war or some unseen filter silences us, the artifacts we've sent into the void might become our epitaph, floating like sheet music for a symphony that never reached its crescendo. Either way, the universe will remember. Long after our sun burns out, the photons carrying our television signals will still be traveling, our probes still drifting, our stories still echoing in the dark. That's the weight and wonder of cosmic storytelling. We're not just observers jotting down notes, we're authors, adding our brief, brilliant paragraph to a saga 13.8 billion years in the making. And like all great stories, it's not the ending that matters most, but the telling. The universe's symphony isn't just playing around us, it's playing through us. Every atom in your body, every thought in your mind, is part of the same grand composition that shaped galaxies and spun stars into being. Think of the last time you felt awe standing under a sky ablaze with stars, or hearing a piece of music so beautiful it sent shivers down your spine. That sensation isn't just emotion, it's recognition, a deep cellular understanding that we're not separate from the cosmos, but active participants in its melody. From the quantum vibrations humming in your DNA to the gravitational rhythms guiding planets, the same laws that orchestrate the universe also compose the story of us. Consider how far we've already journeyed in deciphering this cosmic score. Centuries ago, we mapped constellations onto myths, weaving stories to explain the heavens. Today, we measure the spin of black holes and decode the whispers of gravitational waves. Yet for all our progress, the symphony remains shrouded in mystery. Dark matter's silent pull, the enigma of consciousness, the unsettling quiet of the Fermi paradox, these aren't dead ends, but invitations to listen deeper. The universe isn't a puzzle to be solved, it's a conversation, one where every answer reveals a dozen new questions, and what of the movements yet to come? Imagine civilizations 1,000 years from now, harnessing the energy of stars or bending space-time itself. Will they hear echoes of our curiosity in their telescopes? Will they build upon the harmonies we've begun to trace, or discover entirely new scales we can't yet fathom? The beauty lies in the uncertainty, the knowledge that the universe's composition is unfinished, its finale unwritten. We stand at a threshold, poised between the known and the unimaginable, between the first notes of cosmic dawn and whatever crescendo awaits. So as the video ends and the screen fades, don't let the wonder fade with it. Look up tonight, let the vastness sink in, because the music isn't just out there, it's in you, in the way your heart keeps time with the pulse of existence itself. The universe has been singing for billions of years, and now for this fleeting, extraordinary moment, it sings through you. What will you add to the song? Drop your thoughts below, hit subscribe, and let's keep exploring the infinite together. The next movement is